introduction. Okay, hello everybody. Yes, I said yes. So now we are. There is also someone in the chat that said all good. And hello, online people. I'll try to keep an eye on chat if you see me. But worst case, I'm just gonna take them at the last moment. So thank you for having me here. It's always a pleasure to be back. I hope it's going to be fun. This is actually the first time that I talk about this thing in public, because this is very much work in progress. And it's a combination of a bunch of different strengths of the people that are in the lab so far. So as you can see, the title has a big word in there, which is renormalization and Laplacian too. Laplacian is probably easier to understand. It's going to come up very soon later. But then towards the end, we're going to be talking a little bit more about dynamics and why is this relevant for dynamics and what are we thinking, actually all the ways in which we are not making it work and how we're feeling and what we're thinking about this. Okay, so renormalization. The renormalization that we will be talking mostly about is the good old classic real space renormalization. Okay, so for the physicists, for the non-physicists in the room, the idea is the following. Suppose that you have like a very large system, then you would like to see whether it changes when you coarse grain the system. So if you step away from the system, do you actually see the same kind of statistics? And one of the classic examples is what you see here. For example, you have like these little blocks that are the black squares, and then in there you take all the nodes that you have in there and you create a macro node. And typically, the way you do this is by assigning a new state to the macro node that is some sort of combination of the states of the macroscopic nodes that you have. See, for example, the top left has a majority of blues, and so the top one in the decimated system is going to be blue, and so on for the others. Okay. Now, the idea is that you want to do this, and the full renormalization flow in the classical case, in the lattice case, is that you basically squeeze and then you expand again the system, so the size of your system stays the same, and you keep coarse graining. Then you ask yourself, well, what changes? Does it change, and so on? Where does the idea come from? Well, renormalization has been is present in many different parts of physics, really. But the classical example, especially if you are in statistical mechanics, if you're in complex systems, comes from some sort of spin model. Okay, so the idea is that you could be below at the critical temperature, above the critical temperature, and the theory of phase transitions tells us that around the critical temperature, you should see basically a scale invariant system, because the perturbations scale become power law distributed and so on and on. Okay, so the idea is that if you keep renormalizing your system as you go down, eventually the statistics of the central column stays the same, and the other one is that converge to either completely yellow in this case, or completely or actually average the average of green and yellow in the running case. Okay, so just completely. Okay, so this is the classical case. It's actually funny because when I got the email from Nico and Tim about what you want to talk about, I was like, well, we could talk about topological fingerprints for brains, or maybe these new things we're doing. And then they were like, okay, let's talk about renormalization. And the day after, this editorial comes out on Nature Physics. And, the title is self-explanatory, always relevant. And they have a whole collection of papers describing why, now you can really see here, why renormalization is relevant in many different parts of physics, in quantum field theory, condensed matter physics, and so on. There's one down here somewhere you can't really see, but you have to trust me. It says renormalization group for non-equilibrium systems, right? And in there, they basically, of course, your nature physics, so you claim you're on nature physics, so you claim that you solved it all, but they do say something up there. Huh? So there's a sentence which says, the collection does not cover complex networks where the formulation of renormalization methods is still an open problem. And then there is a reference which actually solves the problem-ish, at least to some degree, and it's a paper that came out like 4 months ago. Okay. So what do you think is the problem with renormalizing a network? So if you have a network that typically, classical networks that we study, they look like this, right? So what is the problem here when you want to renormalize something of this type? The problem is, how do I decide how to basically coarse grain? How do I step back from the network? Okay, so in a sense, if you want really one of the core problems is the heterogeneity. And of course, people have thought about this. There have been many works, and I think this is probably one of the first ones. This was also on Nature. 2007, maybe even, or 5, something like that. And here the idea is that you could build different boxes. Sorry, people here, you don't see me anymore because I'm pointing fingers. You can see boxes. You can create boxes of a certain length. Okay, so you work on your graph, and you decide that there is a box, right? So you course grade that box, and then you can change the length of the boxes that you have, which is basically the number of nodes that you're going to have in there. Already at this level, you see that there is a problem, right? Because how do I decide which boxes, where does a box start, how do I overlap them, and so on. But although there were many theoretical problems, if you want, in how you choose it, it's still possible. If you do this on typically scale-free networks, you end up seeing that in that plot there, as you renormalize, basically the degree distribution stays invariant, okay? Which was really the telltale sign, at least at the time, of how we do that. So this was one approach. Look at the network and try to find out some sort of partitioning way that allows me to do this repeated flow. Another approach, which is relevant and more recent, is, let's say, it's a geometrical approach, and this is work, that goes in the line of, well, Marangela Serrano, Boguna, in part also Dima, Kryukov, and so on. And what the idea really is that you create an embedding. So you basically you embed your network in a geometry of some sort, and then you use the geometry for the renormalization. Okay. So in this case, the metric space that you do the embedding is the S1, is the circle. And the reason why they did this in that case is because if you have an S1 space in which you distribute your nodes, you can induce in the interior of this S1 hyperbolic space, which mimics very well the tree-like structure of scale-free networks, okay? So one solution is that we do it somehow. We make boxes, box counting is typically called that. And the other one is we create geometry. And there are many variations of these things, okay? However, networks are purely combinatorial structures, right? So if you force a geometry on them, we're making a choice. And that's not necessarily what we'd really like to do here. Mm-hmm. And so let me go back 1 second to that citation in the editorial paper that I mentioned earlier, which I claim solves the problem. And this is a recent paper that also was on Nature Physics, in which they had a solution for this problem, okay? Because one way of coarse graining is by looking at, well, you are here with Renault, so you probably should have known about this. You can actually look at processes and the diffusion of processes, so random walks on networks, or like diffusive program networks, and use those properties to define a coarse graining scheme, okay? And in this case, and I'll show you exactly how it's done, and what they were doing is basically they're letting this, like a diffusive process diffuse on the network, and use the equivalence between nodes induced by the fact that you have, by the diffusion process, to define your discretization. And you see that even in this case, they actually show as evidence. I mean, this is a paper, a plot from the paper, that, if you do this on that was a Barabasi-Albert graph, I think, your degree distribution stays roughly invariant throughout the repetition of this process, okay? Now, this is very nice, but really the point here, it's not in the degree distribution there or the invariance, presumed invariance of that, but it's really in something else, right? It's in the spectral entropy, or at least, or the susceptibility really is going to be the heat capacity. So what do I mean here? So the one that you see up there on the left is the definition for the spectral entropy, where that L is the classical graph Laplacian that we all know and love, I assume, or if you don't, it's the diagonal degree matrix minus the adjacency matrix, normalized appropriately. In this case, you don't even need to normalize it because the partition function is going to do the trick for you on the bottom. And then you have this entropic susceptibility, which really is the heat capacity on the bottom, which is the derivative of this, okay? And the idea is that when you have a heat capacity that is constant in a certain set of this parameter tau, here, it doesn't change, you have scaling invariance. Why do you have scaling invariance? Well, we say that there is scaling invariance. Well, because if you look at the exponential in the first formula, right? So you're diffusing on a network, and this tau parameter is the parameter, is the diffusion time, dominated by the Laplacian. So if you're saying that the heat capacity doesn't change throughout, what you really are saying is that the system is being seen by this diffusing parameter as the same across that diffusing range of diffusing parameters. Okay. You can do this. You can actually go and check. For example, if you take the grid, which is the same as before, you basically play this game. You see the plot in the center. That's the heat capacity as a function of various steps of this renormalization approach. And forget the last plot I'm going to explain in a second. And then the same thing happens if you do this on a tree, which is a very natural renormalizable thing, because you can think of a tree as like some sort of fractal that grows. And this idea of that it's going to come back, and you see it's natural to go from here to here, right? Because it's basically what you do when you grow a tree in reverse. There are conditions that you can actually find that derivative of S over log tau for that to be flat. And one of the conditions is that the distribution of eigenvalues of your Laplacian is power law distributed. So you can be power law with a non-zero power law power exponent, or with a zero exponent, like in the case of the grid, but it's still there. So in this case, everything seems to work well. Yes.
So it works in the situations when distribution of.
So the thing is that if you want this condition here, this to be flat as a function of tau, this is true if you have not only if and only if, but it is sufficient for that to be flat in a certain regime, a certain set of parameters. So basically, you see that there is not flat everywhere, but there is a region in which is flat. So if you have the kind of distribution, same thing for the power law, having something like this is going to give you an interval of tau values in which the whole thing is flat, okay? I mean, of course, these are all finite systems, right? So at the beginning, you only see nodes. At the end, you only see one node because you have, of course, clean everything out. So you don't have this kind of infinite effect, right? But in general, this would be the. And then, you can actually show that in this case, again, if you do this for a set of networks that they have, these are two gene interaction networks or protein interaction. This is the human interactome. That's an internet graph. If you do this game, you again find, that as you normalize, in this case, the degree distribution doesn't change. This is actually interesting because they keep showing the degree distribution changing or not changing actually in this paper. And there is a mixture. Actually, this is something that it takes a little bit of reading the paper to understand that this is the catch thing that you put on the paper, but this is not really the point. The point is in the heat capacity earlier on, okay? Why am I stressing this point? Well, because when you go to higher order systems, which is what I will be talking about mostly in the future, this becomes harder because if I ask you what is the degree distribution in a hypergraph or a simple complex, then you should ask me, okay, how do you define degree distribution? What degree distribution? Degrees of what? Okay. Now, why do we want to go here? Well, two reasons. One, it's fun. Two, topology makes for really good pictures. Three reasons. It's also a property. If you have a topological structure of your system that is non-trivial, it's very robust. The classical joke is, okay, if you have a mug, topology tells you that the topology of the mug is the same as the donut. Then the question comes, okay, why do you want a donut if you have a mug? And the answer is, well, if you have non-trivial topology, then probably the topology information is important. So you want to preserve it, and it's going to be preserved. There's also another story, and this is for the students here, that probably should know about. So if you look at the founding myth, the origin story of graph theory, really, the problem of the Königsberg's bridges, that was actually acrobatic to say, it's a topological problem in the true algebraic topological points description, right? Because you don't really care about the geography, the relative position of the islands. You only care about how they're connected. You can actually shrink down all the islands to one node, and then you only care about the interaction. So really, graph theory is zero-dimensional topology. Everything else is more interesting. So what do we get on top of that from generalized topological objects? And now in the rest, I'm going to be talking about simple complexes, but really everything I'm going to show you later can be easily generalized to hypergraphs. Just that in simple complexes, everything is simpler to define because all the pieces, it's like a Lego castle with all the bricks there, right? So you don't have to dodge the Legos that are not there. What is the big difference? The big difference is that if you can have a triangle that is not just the sum of the edges, and then you can have a tetrahedron that is not just the sum of the triangles and so on. Okay, so in general, you actually have terms that look like this. Okay, like this is what we call a K-simplex. It's a sum of k plus 1 nodes. A set. If you do this in a metric space, those points should be independent and so on. But in an abstract simple complex, it's just a set of them. Okay. Now, if you've done a little bit of statistics, especially information theory, or if you've been following your recent C3 workshop, for example, you should be familiar with this other writing of something that looks the same, right? These are multivariate information distribution. So you actually look at distribution, joint distribution of a set of different variables. They look similar, and they should look similar because they're both intrinsically higher order. Okay, in the way we describe. What do you get when you actually have something that is a simplicial complex or a hypergraph there? Well, the point is that the information, you can describe the bits, the bricks that compose the simplicial complex in this way or in this way if you want statistical description. But the additional topological information you have there is that you have a hole in there, okay? And this is actually some sort of intrinsically non-local information that doesn't just come out from the set of things you have, but it actually comes out from how they're put together, okay? Unfortunately, we tried to use the diffusion process because, of course, this is where we're going. We have a diffusion process that is defined as simplicial complexes or hypergraphs, and that would respect the topology, but then there is a problem with that. I'm going to show you what it is. So now the question becomes, okay, which diffusion do we want to use to do the same game that we did before on graphs, but do it now on simplicial complexes, or there are sparse version, they're like flexible version hypergraphs, okay? Now, I assume everybody will know what a boundary operator is, so I wrote what is called the Hodge Laplacian in this form. Everybody knows what a boundary operator is? So the boundary operator is an operator that takes a sum of triangles, for example, formal sum. You take the boundary of that and gives you the boundary of them. So for example, if you have one triangle, the boundary of the triangle is going to be the three edges. Okay. If you have a circle, or if you actually take the three edges that you get, taking the boundary of a triangle, so the only three edges, you're going to find zero, right? Because if you have something that is closed and there is a hole, it doesn't have a boundary. Circle doesn't have a boundary. This is actually a general thing. The boundary of a boundary is always zero. Okay. Now the operators you find there, you see there are boundary and co-boundaries. So they are going down from, say, triangles to edges, or from triangles up to tetrahedron in this case. Okay, if you're starting from there. So really, this is telling you this is a generalized Laplacian that doesn't only operate at the level of the nodes, but it can operate at the level of the edges, the level of the triangles, and so on, right? So when you think about the diffusion process on normal graph on nodes, you can only go up to an edge and then down on a node. If you are starting from an edge, you can go down to a node and up to an edge, or you can go from the edge up to a triangle and then down to the edge. Okay. Now, sorry, I thought that this was common knowledge. So Hodge Laplacian, please, let me introduce you to this thing. One of the beautiful things about the Hodge Laplacian is that the kernel of the Hodge Laplacian in a certain dimension has the same dimension as the number of holes that you have in a simplicial complex. Okay, so the homology of simplicial complex is the same as the null space, dimensional null space of the thing. There is a problem for us that this thing is not diffusive. It's actually reactive diffusive. There are some very esoteric formula, the Boechner-Weizenberg formula, that tells you that the Hodge Laplacian can be written in two parts. One part, which is called a rough Laplacian typically, plus a curvature term. Okay, the curvature term is what's called that's the Forman curvature, which you might have seen in the literature. This one is funny, right? Because it's a graph-like Laplacian, so it's like diagonal term, degree term minus an adjacency, but it's signed. Yeah, so we actually don't really know how to manage this. So what we do is we cheat. We basically design this guy. We throw away the curvature. This is gonna be word for home, future word of the reader. And we take this guy here and we remove the size. We end up with actually a graph like proper graph like one. But the point is that how do we do this, right? Because we have an infinite ways of.
So the
yes.
sign graph like Laplacian. So
yes.
Is it related to the sign Laplacian from graphs, or is it different from it?
Formally, it's the same object, but I don't know. I mean, you could associate a graph that has that Laplacian, but we didn't really know how to go about this because we wanted like the normal exponential diffusion, right? So if we had like two terms, the one part would completely, explode, so we didn't really know where to go with that. But yes, I mean, it is formally a sign Laplacian the same way you would have on a graph.
Okay. There are a lot of things that I know about those Laplacians as well, right? Also,
yeah.
We
tried to use that, but we didn't really know how to go about that. So we cheated, but we cheated for another reason, because we did this, but then actually what we wanted, we even tried to get a bit more general, right? Because if you start thinking about adjacencies, you can have very different types of adjacencies, right? You can have, I mean, yes, but that's not what we did. But we could also talk about that. Because one thing you could do is you can start saying, well, okay, my units are nodes, 0-dimensional, and I see which nodes are attached to triangles. So I change my adjacency between, my whole singular complex inside in a new graph where, my nodes are the new nodes are the nodes, but they're attached only to each other only if they belong to the same triangle. Or you can do the other way around, for example, or you can play with those labels as you want, right? You could take the triangles as your nodes and then attach them if they share a node. Well, sorry, an edge. One is an edge, okay, in this case, or a node. Okay. So in general, you end up with a family of these potential graphs, which we call JKM, which are constructed from the original simple complex or hypergraph. As you see, we can do the same here, it doesn't really matter. And then for each of these guys, you can associate its normal graph Laplacian, the unsigned, the classical one, okay? And then, of course, you have your normal diffusion there. Where we lost a minus? No, the minus is there, okay? Nice. Okay, so now that we have this new thing that can be defined, as you can see, as multiple parameters, right? Because we can define it at the level of the nodes, edges, triangles, and we can decide what we count as adjacency for each of these orders, which is the M. The game is the same. And of course, you can try to start and validate this. For example, the first thing you do is that you build the equivalent of a tree. And this is a pseudo-fractal, simply complex, in which you basically fill up the triangles and so on. And then what you can see here, when you look at it at the simplicial, at the heat capacity, is that, as you go, these are the different possible Laplacians, but the only one that really gives you some sort of flatness, even for a simple small one, is this L21, which is the one where you have triangles as units and adjacency through edges, which is really describing the growth process of this pseudo-fractal, right? Because you're adding triangles, you're attaching them to edges. So it's actually capturing the fractality, if you want, of the structure here. Of course, all of them, all of the Laplacians will have a heat capacity, but the ones that we're interested in this case are the ones that show you this kind of plateaus, because the others, whenever there is a peak, it just tells you there is a scale, just seeing that scale. Okay. It's like, if you want example 0, for the factory work, I actually forgot that I had a good explanation for the actual visualization. The other one that sort of goes kind of close is the one in which you look at edges attached to triangles. 1-dimensional, 2-dimensional. Okay. But it's not as good as you see, right? Because really the units of the system is. So of course the idea there, right, is that we go in that direction. we can use these kind of tools to fingerprint systems that we have. Suppose I give you a hypergraph, I give you a simple complex, and you run all of these, and then you can try and find, for example, exactly which one, if under any of these lenses, Laplacian renormalization lenses, one is scale invariant, one system is scale invariant. Something that I haven't really told you is exactly how this works. And the working part, it's a little bit trivial, but I'm going to give you the sketch. So you start with your system, you compute this raw, which is that it's the same matrix as I showed you before. It's basically the e to the minus tau L divided by, it's basically this here. So I thought I've written there. So that's really raw log raw. And you have a matrix that looks like this. And then you have to choose some tau at which to cut, because you basically decide the function, that matrix depends on tau. So you choose a certain tau, and there are ways to do this. You end up with a matrix, and then basically just threshold these of some statistical level. And then you end up with a binary adjacency matrix between your units. And the binary adjacency matrix between units, it basically tells you which edges correspond, for example, in this case, edges or triangle units belong to the same macro node. Okay? So it's a way of identifying the macro nodes from the diffusive process. Okay? Once you have that, you basically collapse the ones in the same, the blues here, the orange here, you collapse them together. And you can see that it's not easy to understand how you do it when you go higher order. So that's the tricky part, which I'm not gonna explain because it's just technicalities. But for example, in this case, the pseudo-fractal, you see you go from here all the way down here. So even just visually, you get the right result. Okay. Good-ish? Yeah. Okay. So on the pseudo-fractal, we already saw that this is nice. It works, but we would like something more. And for example, we would like to see whether as you make this grow, another test that you can do is that you can make this fractal grow and grow and grow. So the larger it becomes, the more normalizable it should be. And you actually see this, right? Because basically, as you go ahead, this thing continues. And then you can measure, you can define the speed, basically the how flat, how large that interval is. Yeah. Don't worry about the definition. It's just it's a very convoluted definition, but it's really just how flat this bit is. And then you can see that, for example, for the CO2, which is PO2, it's very little flatness. For the C21, P21 over there, it's larger flatness. Yeah, so on, right? So you basically have these kind of like polar plots that tell you which are the best, let's say, levels of these renormalization lenses that give you, the flattest part, and actually tells you which is the process that is the dominant in this case, right? And even visually, again, if you do this game again, if you renormalize with the wrong Laplacian, you have destroying the structure, L01. If you renormalize with the right Laplacian, you get something that looks even visually correct, okay?
Another interpretation of this is it's the least scale, the one that's least dominated by a scale, is that right?
Well, yes, it's the more invariant, scale invariant in this sense. Sorry, yeah, that's what I mean. Actually, so this plot is showing you that the bigger you make this is the fractal, the more invariant it becomes, of course, right? Because there is more space for the renormalization. But here we're not really renormalizing, we're just like looking at the heat capacity directly. On the bottom, if you perform the actual renormalization, you see this effect, okay? Again, one can play this game again and using, for example, network geometry with flavor, which is a model by Ginestra and collaborators in which you build the different, you can build from nodes, from edges, and so on. You can get all sorts of weird structures, including manifolds. And then again, you see, for example, if you go from time to small dimensions, so you build with edges all the way building with the radar up there, the Laplacian that gives you the scale invariance is the one that is corresponding to the higher order structure, right? And it's actually, very, very, encouraging. Again, here is an example in which if you normalize with the good one, you get a good structure. If you get that one, it doesn't work. Okay. Finally, before going on to the dynamics part, which I think it's where the problems really start, of course, you would like to try these on data. Okay? For example, if you take the Enron data set and you play this game again, this plot that you find here looks like this, okay? Now, the problem when you start using data is that you don't really have a prior, right? So you don't really know what you should expect. You find something, and this is telling you that the most scale invariant structure that we find, at least if we cap these at triangles, is the one where you're attaching triangles by a sure. This is what it tells you, but is this really meaningful? Well, we don't know, but there is something that you can do to at least have an expectation in this case, which is, as I said, if you remember, for every of these levels, you build a Laplacian, so you have a graph, and you can actually randomize the graph. So you basically can take the associated graph, normal graph, randomize it as a configuration model, and then recompute everything, okay? And then you see it, for example, in the case of Facebook, the randomized version has the same properties as the data. The randomized degree in the bottom. And in the other data sets, you have some specific dimensions that are more important. Of course, then you can actually push this forward. I mean, this is the part that is taking a lot of time because all these things are very heavy to run. You can take a bunch of these data sets and then using those, in this case, 6 numbers, but you can also go higher. You have like basically a 6-dimensional vector for each data set. You can create an embedding, and you can see that, for example, you get all the ecological ones here, the brain one here, the transportation there. It's actually cute. It doesn't really. I mean, it's nice to show that we actually reconstruct sort of known information using this fingerprint of how scale invariant a network or a higher order network is at various levels, but it's not particular. I mean, you could do this without using this old technology, okay? Point is, okay, how is this relevant for dynamics? Yeah, so why do we care? Why do we care? Well, we care because, so far, we've really spoken about scales and its scale invariance. And, so the picture is the one that I showed you. Oh, sorry, I forgot this. But the thing that we would like to discuss is what happens if I have a dynamical system on top of this. Now, I can already tell you that we don't know the answer for the higher order case, but I can show you something that we do know about graph, and then can tell you what we are trying to do for higher order case. Why we're interested in this renormalization? Well, if you remember earlier, I said that the classical interest in this renormalization approaches is to find basically, you know, the exponents, universal exponents of the system, of the process that you have when you have this kind of scaling invariant things. But there is also another reason, right? Because you would actually try to see whether you can find emergent scales from the system, dynamical scales that then behave at the same time. This is a classical example of the group of birds that are flocking around, and at some point, they're better described by the variables of the flock, the macroscopic variables of the flock, rather than the variables of the macroscopic variables and so on. So this is something that's called causal decoupling or emergence of scales. So the idea is that the macroscopic variables, these V and Vt up there, do not depend anymore really on the macroscopic case, in the sense that they do depend, of course, but you can basically compute stuff just using those without requiring macroscopic definition. A little bit like when you go from statistical mechanics to thermodynamics. So this is the, if you want, the generic idea. How would one go about measuring this on a real system? Well, that's the problem, right? So the way we know how to do this on a graph structurally. So we start from a graph, we normalize, and that other G is the Laplacian renormalization graph, renormalization group. We also need the dynamics, right? So we would need some rule. Say, well, when those red nodes become one node, how do I compare the information? Okay, so if I have these two elements, I can actually go and go over. And the interesting thing is that it works very well. I'm going to show you in a second. But we need also a null model for this. If you have a sort of to see whether it works. So what we did in this case was we have a network, we have a microscopic dynamics, so Glauber dynamics or contagion, doesn't matter. And then we have a null model, which is the same dynamics run on the renormalized network. So in one case, you have the microscopic network, the dynamics, and you have a rule to aggregate the microscopic dynamics. In the other case, you're running the dynamic itself on the normalized graph, okay? On the coarse grain graph.
Can I just
yes?
Am I correct that if you want to run like the random dynamics, the Laplacian dynamics, it would be equivalent by construction?
Yes, because that's a diffusion. Exactly. That's the way it's been.
The question is, if you run another dynamics,
that's exactly
based on
exactly. Okay. Because what you're because I mean we did this with, I'm going to show you the plots for the Glauber dynamics, for the Ising dynamics, but you can also do it with Kuramoto, you can do it with contagion, not diffusion, but actually contagion, and the results are basically the same. Okay. So what you find is that, for example, if you have a system that has a scale, right? Because here we are creating this is a stochastic block model, so we do know that we have a scale. What you end up having is the specific heat looks like this. So you have one scale corresponds to the system that is starting to see the blocks, and then this is basically when you start seeing the whole network as one. And this other line here is called the expected peak. And the reason why we call the expected peak is because if you coarse grain the system at this stage, we find exactly the same number of communities that we have up there. Okay. So actually the system, the diffusion problem, starts seeing the diffusion a little bit before you would find the exact numbers. Of course, when you start perceiving that there are those communities.
So this one would not be renormalizable.
This is not renormalizable.
It doesn't have
but in fact, we turn it the way around. Right? So the point is that we renormalize here, and then as we renormalize, and in here the aggregation is the Ising dynamics, and then we do majority vote, like in the original lattice one. You know, remember the blue and red at the very beginning. And as you do this as a function of tau, so if you normalize going forward, you find something that looks like that. Now, let me explain what is that TDMI. TDMI stands for time delayed mutual information, and it's the mutual information shared by the variables xi and xj at t time 1 with their pasts. Okay, so that information there is telling you how much you can predict your future from your own shared past. Okay.
What are INJ? Two
neighbors, yes. Two neighbors in the coarse grain representation. Okay. And then what you see here is that if you go forward, there is a specific, at some point you step up and you find this like peak, and then it gets flat. And that's actually where you would expect to see that. So really what you're saying is that the system diffusing, the Ising model with these couplings is going to tell you that there are those partitions from there. The other interesting thing we want to see here is that this predictability, this kind of information at that scale in the system starts increasing exactly when the system, which is the actual peak, when the system starts seeing a little bit. Okay. And the null model that I described earlier, the one when we run easing directly on the coarse grain one, is just shown here to show you that you don't really have that effect. This is just really this thing to check. Okay, so we can do this. It's very nice. It works. It's pretty. And that's what we call emergence. That would be the definition of an emergent system, because you actually have that at that scale, the system can predict itself better than it would at a microscopic state. One of the many definitions of emergence. Agreed. Okay. Fernando would agree with this one, although he would like to have this done in a different way. Of course, depending on the structure you put below, you have different outcomes. If you have this hierarchical classic block model, you find the same jump when you find the communities, and then don't really see it, but it's there. There's another jump for the other level. If you do this on another Shreni correctly, you don't find anything because you shouldn't have any escape apart from the nodes and everything, right, in the system. So it works very well. Okay. So summing up, we have developed this renormalization scheme for higher order structures. It's one of the possible ones. Maybe we can also do the sign one, but this is definitely one of the possible that gives you those two indices, right? So the unit, the first index, and then the definition of adjacency, whether they share a node, an edge, and so on and so forth. Actually, in the paper, this is going to be called L mu nu, because the first order is called Marco Nuris, so it's going to be M, whatever. We validated this on scale-free synthetic models. I find it very amusing. I don't know why you don't. There is evidence of some level of scale-freeness in the data. And also in some cases, we actually can detect that it's not really there with respect to the null model, okay? Now, if I have another 5 minutes or so, 10, I don't know, 5, let's say. Again, the question is this relevant? Okay, so for higher order dynamics, okay? I showed you a case. So I started showing you how we do renormalization on graphs. I show you that we can do structural normalization on higher order systems. And then I show you that if we do structural normalization together with dynamical process on a network, we find something that is non-trivial, okay? And the question is, does it matter for higher order dynamics, okay? And for higher order dynamics, I mean two different things. So the first one is systems that have higher order interactions by construction. So instead of having me sneezing on you or me sneezing on another person, it can be a group of 3 and 2 people sneeze on the other person, and there's a different effect, so like peer pressure kind of thing. Or dynamics that are generally defined on the edges, on the triangles, okay? I don't know whether I'm gonna have time to show you everything of this, but the short answer is no, we don't know yet, but we have some ideas, okay? And just to give you it's like a very rapid look at what higher order models look like. So this is the example of the sneezing in a group, or actually of group pressure, right? So the idea is that when there is a triangle with two orange ones, it's the probability that the other blue one becomes orange is larger. And the cute thing here is that you end up with like interesting bistability systems that you wouldn't really see in a normal contagion model. And if you slightly generalize the system, you can find all sorts of weird effects like mirrored transition, that first order transition that becomes mirrored. And actually this mirroring here corresponds to localization. So you have overall, the system is not infected anymore, but you have a localized of a very tiny C that survives in the larger phase. Process localizes, that's the thing. Another example is the one of synchronization. Now, you probably are used to Kuramoto model, where your variables are on the nodes, and maybe you can actually couple them with triangles and so on. There's another version, which is in Estras and Anna, and so on, in which you generally, the variables move from the nodes to the edges, to the triangles, and so on. And if you do this kind of simplicial Kuramoto models, you find all sorts of weird, interesting patterns. For example, this is just a set of chains of edges with one triple edge here. So there is a node with 3 edges, no triangles, no nothing. And you just run this process and you see you have all these kind of like traveling waves. And this is to the fact that you have a non-manifold point here. Do the math, and then if you increase the coupling, you can find weird effects. For example, that you have the manifold, non-manifold like part, so one-dimensional part that freezes. Then this other part here, because they are topological circles, they continue going. The video started, so that freezes again, and these guys keep going and going on. And the reason is because you have a hole in here, and that gives you the cyclic symmetry. And in that same system, if you actually crank up the model even more, you can find negative order parameters. Which actually means that you end up with something that looks like anti-correlation. Okay. You have all sort of weird effects that you have there. This is another example of high-order fit. Interestingly, in the spirit of scientific research, we tried to run this on connectome data, and it turns out that the stupidest model, the one just on the edges, predicts functional connectivity. This is ours, this is the edge model, better than all the other models that exist, including the most recent by the Sporns lab that has many parameters. Now, that model is biologically believable, ours is not, but the fact that it's a very simple model based on edge dynamics or on node dynamics does better, even though it's not much better. It's interesting because it probably tells us about what is the real process that is going on there. Okay, and of course there is a third type of processes which some of the work has been done. So here by Renaud and so on coordination, norm evolution, when you have groups that decide whether to agree or not. Okay, now these are an example. I just want to give you an overview for people that have never seen it. What is the problem here when we talk about renormalization with these dynamics? The problem is that we have an additional dimension, an initial degree of freedom with respect to the graphs, right? So before we had systems with dynamics, and then we're of course grading. So we only had scale. But now here we have two elements. We have order and scale, right? And what order is the dynamics defined? How do they interact with each other and so on, okay? And of course, this snowballs down to a bunch of other things. For example, one of the questions is how much information is there, right? So can we actually use this information to reconstruct, to predict the system? And in the case of high-order dynamics in particular, this should be specified to how much information is where, okay? So what do I mean by that? I mean that suppose that you run one of those weird Kuramoto models that I showed you here, and you are trying to figure out whether you can predict where these triangles are and where they're not. And if you run this thing and you measure something that's called O information, and it's like a very fancy high-order mutual information, don't worry about that. In a simple system, you actually find high values for the correct result. See what is orange? The reason, but then if you go to a larger system, then it's not there anymore. Okay, just it gets completely destroyed. Now the question is why? Well, the reason is that the quantities that we use to measure higher order 3-body, 4-body, 5-body correlations, they really also have the echo of all the lower correlations, right? So the question should not be is where, but is from where. Okay. So one possibility is, and we don't really have a full answer to this. Okay. One possibility is that you can try and constrain the lower dimensional correlations, and then use that to clean the data, right? So you basically look at the predicted versus the one that you measure. And in a specific case, when we have Gaussian variables, or at least we pretend to have them Gaussian variables, you can actually measure this O information directly from the correlation matrix, the pairwise correlation matrix of the system, right? So now imagine that you have a system, you have a time series, you suspect there are higher order interactions there, so you can measure this information, you can measure the pairwise correlation, you can predict from the pairwise correlation matrix what you would see in terms of information if you only had the pairwise one, and then you can compare them, okay? So then the question becomes, can we use this thing to separate lower and higher order contributions? And the question, and then the result is yes, in some cases, okay? In this case, what you see here are results from the contingent dynamics up there for the contagion, the sneezing contagion, for contagion. And the distributions are for two simplices, so the actual triangles, cliques, which is just the edges, or 3 nodes taken randomly. Okay. And then what you see here are the distribution of values for the real, so the frequency base, the blue is the one you measure from data, and the red one is the one that you predict in this way. So you basically just take the covariance matrix between the nodes dynamics, you predict what information you would see at the order 3, if you only had those. Okay. Up there, you see values of the parameters, and basically when the lambda delta is below 1, you don't really have a big effect of triangles. And what you see is that if you increase, you go in the direction, nothing happens. When you go above 1, there is a wall of this distribution just up here. Okay, so really only in the case where the triangles have a role, so only in the case where the triangles have a role, because the effect of the effectivity of the triangles is very large, and you're looking at triangles, you actually see this effect. Yes.
How did they even that swap?
Too hard to know.
You're fine.
Yeah, I know. Well, you already get it like 2 or 1.5. It's just that it's not so clean. But then actually this was the first thing we did. Then we did another thing, which was this, because now you're computing, you can create one value for every triplet that you have, either a triangle or not, and you can plot them one against each other. And the value parameters are the same. And the important bit that you see is the fact that only here this green guy separate from the other ones. Okay, so the idea is that here you can actually see the distribution. And it's funny because, well, the guy, the student who's writing this paper, prepared this paper, is called Cosimo. So we refer to these as the Casimir effect instead of the Casimir effect. You can do this also with dynamic law information. The result is actually stronger, but the idea is the same. But really, the message that you should take home is that actually, to your answer, this is the answer to your question. So you can actually look at the divergence, Jensen-Shannon distance between those two distributions, the one on the simplices and the one on the cliques. And then what you see, what this plot is telling you is that in this regime, when lambda is small enough and lambda delta is large enough, then you can actually see the difference. When they're both small, both large, or somewhere up here, you don't really see anything, which actually tells you that dynamically, the expectation would be that you cannot actually reconstruct which high order interaction mechanistically you have there, just from a time series. Okay. So again, summing up, and I'm done. This is the things we said earlier. So we ended up having, some initial steps for discrimination. So we're good, but we're not really done. Actually, so the first to do that we have is understanding these potential effects between sort of higher order, between order and scale, right? Because we haven't done anything there. Then there is another problem, right? Which I have not really talked about. So I always said, if I have the structure and I have dynamics, then I can do this game. If you have brain data, you don't really have a structure for example, third order, if you compute series, time series, or other information, because you only have the connector, which is low order. You can use that. If you have time series from financial data, you don't have a structure on it, you just have the dynamics. Okay? So how can actually sort of put the two together? And the state of the art currently is like this. So we don't really talk about this. We are trying, but if you want to put a name on this, can we actually have techniques to extract candidate structures below that we use, which really is about what is the error or can we estimate the error that we do with the estimation from the dynamical part of what we would have in terms of the structure. This is something you can do, of course, right? Because you can do the experiment. You take a structure, run the system, and so on. But of course, you never really know whether the point then in the reality you're gonna get that. And you also have to keep in mind that the additional complexity is basically that last plot I showed you, right? Because it could be that you are in places where you cannot tell the difference between a hypergraph or a graph, so on, because the dynamical parameters of the system, the dynamical regime, if you want, is such that you cannot do that. Okay. So with that, these are the faces of the people involved. The guy there just graduated is the Casimir effect, and the others are other people in the lab. If you are interested in these, and if you want like a wider exposure, we have a perspective. We also have a book about this, and also people in the room contributed to this. We're not hiding anymore, but we're going to be hiding again soon. There was like a hiding PhD postdocs, but we're doing interviews now. But just talk to me, and if you're interested in the slide, they are like just down here. Okay, thank you.
Thanks, Giovanni. Are there any questions in the room or online? We might have to manage the audio, but you can just raise your hand or try to speak if you're online and want to ask a question.
They seem silent.
Yeah.
Yes.
So using the Laplacian for the
Yeah.
renormalization, does that actually have like a dynamical assumption that you have some kind of diffusive process on your network?
Yeah, of course.
So could you replace that with like, let's say you had an oscillator like the promoter model, when you know that you have like synchronization, maybe that's more important to cluster nodes together rather than the Laplacian.
Yeah, so the original, okay, that's actually interesting because the original, so if you want to do exact normalization, you could do the momentum space normalization instead of real space, which means that you take, your Laplacian, for example, and then you write it in the spectral representation. So the sum of the eigenvalues, both bracket and so on, and you basically chop off the large ones, right? So you're basically chopping off the fast modes in that case, and you only keep the slow one. So this is a way which you're basically doing. This is the classical momentum space renormalization. You're basically integrating away the slow mode, the fast mode, and keeping the slow one, which is basically something similar that you would do here. So that's one possibility. What you would, and actually goes in a little bit in the direction of what you are saying, right? Because those would be the natural modes of the system. If you, yeah, I mean, you can do whatever, because even if you have, I mean, as long as you have this eigenmode decomposition, then you can do this kind of game, right?
Yeah.
So definitely that's something that could be done. I was thinking about this. I don't know if you've seen the latest work by Giovanni Petri, which is looking at like stationary waves in brain dynamics.
Yeah.
I was wondering whether something like that could be done there, whether you could actually have that. But the whole point there was the whole point for her there was that each of those frequencies, each of those modes really had a, if you want, a functional meaning, right? So you wouldn't really chop them off. But yeah, like the format you can do it. I'm not really sure what do you do with it? You know, how do you interpret it? But yes, of course. Yeah.
So one step that they use, if I'm right, in this like renormalization paper is because indeed you can do it in the momentum space, but the thing that they still want to identify nodes, right?
Yes, that's the problem. Yes.
It's kind of like ad hoc somehow construction. The way I understand it, where the construct, if I'm right, is kind of like correlation, like the matrix of rho ij, like
Yes.
from I to j.
And then they cut somewhere.
And then they basically use that to binarize it, and then they look at the connected components. Is it the way?
Yes, and those are the Cardan of macro nodes.
Yeah, which is kind of a funny thing because in a way they do like a momentum renormalization, but yet they find a way to impose that it's constrained on a small set of nodes. And that's always something I found a little bit, I wouldn't say disturbing, but I don't really understand, like the logic behind it.
Okay, I don't completely, even though Tommaso is also in the paper, we've been fighting about that. The way, so there are a bunch of problems there that really all sort of hinge in the end on how you choose the tau star, which do the step, right? At least they're related to that. So for every step.
The tau star comes from where?
Yeah, but how do you choose that, right? Because they say that they do that, but they don't really do that in the paper. They just figure out. So the point is that when you want to compare between, for example, when we wanted to compare different lenses in our case, what we did, we chose for the different Laplacians that we had in this case, different taus that gave you the same reduction in number of nodes. So at least you had the same shrinking, and then you can compare them. Okay.
Shrinking is difficult because it depends on you need to for each time look for the connected components.
Yes.
And stop when you find exactly the right number of components.
Or something very close, yeah. Yeah, no. Computationally it's crazy, but at least it was let's say principal way of comparing the different words. Now, I agree. The problem is it doesn't work now. I don't understand about relation to normalization. Aerodynamics, can you explain more? Yes, I'll try in a second again. Let me finish answering this question. And so their problem here was that, so if you do only momentum space normalization, you don't really see what's happening to your structure, right? So you're blind to that. And that's the reason why they were doing that. And you know, in here, in a sense, we don't even need to do the normalization because we just look the heat capacity. We already have basically the full picture, and all the invariants that you get, those P's and so on, they really are just about that spectrum. So another check that I skipped here is that what you could do is say, okay, I choose this, I do this shrinking, and then I recompute the heat capacity, and I see if the heat capacity that I get after one step of renormalization is close to the original one or not, in the case of a scale invariant system. And if you do it this way, in the right way, you get it, otherwise you don't. Yes. I'm not sure how far back do I have to go to the normalization hydrodynamics for the question there. It's a long question. I think the take-home message is that you have one more degree of freedom that you have to take into account when you want to do normalization in hydrodynamics, because you don't only have the scale of the normalization, but also the order of the interactions at which you're doing it. And that in some cases, you might not be able to distinguish the dynamics that you have from a low order dynamics. And that is a problem if you're trying to reconstruct, if you don't have the structure already. I think those are like take-home messages, like shrunk down if you want. It's okay? Yeah. So.
Great. Let's thank you again.
And thanks everyone who joined online. We'll see you next week for the last seminar of the term. So yeah, thanks everyone.
Thanks.
Bye.
Thank you.
And it's been running smoothly.